You remember from Friday that we have a situation in physics 30 where charged particles are speeding up or slowing down that is much like a situation that we had in physics 20 where a car was speeding up or slowing down. Take you back to the physics 20 lesson for a second here. If we have a car at the top of a hill moving at a speed, let's say of 10 meters per second, on a hill that is, let's say, 100 meters high, the car will speed up as it goes down the hill, and it's going to reach a certain speed when it gets to the bottom of the hill. It's going to reach a smaller, albeit a bigger speed than 10 meters per second when it's halfway down the hill. Let's say that in this question, we want to find the speed that it reaches halfway down the hill. How would we do this question? Take it back to a year or several months for some of you. How would you find the speed of this car in the middle of this hill? What kind of energy do we have at the beginning of this problem? Yeah, there's potential energy. And there's potential energy because there's a height. Not because there's no kinetic or not because there's no kinetic or whatever. Potential energy is based on height. If there's a height, there's potential energy. So we'll say mgh, initial, and Ariel said there's also kinetic energy. The kinetic energy is not based on the potential energy. It's just simply based on whether there is a speed or not. So we're going to say that there is potential and kinetic because there is a height and there is movement at the top of the hill. Now, when we reach not the bottom of the hill, but when we reach that point halfway down the hill, is there still potential energy? Yes, because there's still a height. We're going to say it's mgh final. Is there still kinetic energy when we reach that point halfway down the hill? Dak? Still kinetic energy? Or is there kinetic energy now? Yeah. How does the potential energy partway down the hill compare to the potential energy at the top of the hill? We don't even need a number for it. Bigger or smaller? It's going to be smaller. The potential energy is smaller. In other words, potential energy is decreasing here. What about kinetic energy halfway down the hill? It's increasing. What about the total energy? It stays the same. In other words, you've got a conversion here of potential energy to kinetic energy. It doesn't mean all the potential energy is gone and that you just have kinetic energy at the end, but you have less potential and you have more kinetic energy at the end. Got it? All right. Well, what about this situation? What about when I have two charged plates that causes an electric field? Let's say the left plate is negative and the right plate is positive. Let's say that we've got a negatively charged particle starting this way, we'll call it down the hill or across the gap at a speed of 10 meters per second. What's going to happen to this charged particle? It's going to speed up or slow down. It's moving at 10 meters per second to the right. It's attracted to the right, so it's going to speed up. The other way you can think of it is this. You have an electric field pointing this way, away from the positive toward the negative. Which way is the force on the particle when it's a negative particle? Against the field. A positive particle experiences a force with the field. A negative particle experiences a force against the field. So it's moving to the right, and there's a force to the right. It's going to speed up to the right. Well, that's like a car going down a hill. Picture it as a car going down the hill. Picture this red car on fire, no insurance, no driver, no passengers going down this hill. What kind of energy does it have when it starts at the top of the hill? Well, it has potential energy, except the potential energy this time isn't going to be mgh. The potential energy this time is going to be what? Q times, anybody got that? Q times V. Be careful, not QE. QE is electric force. QV is electric potential energy. Okay, keep those straight. QV plus, does it have kinetic energy when this car is moving at 10 meters per second at the top of the hill? Yep. So it's got 1F mv I squared. Well, what about when it's halfway across there? What about when it's halfway across that potential difference of 20 volts? Does it still have potential energy? Still have potential energy, Sydney? Yeah. Yes, it does. But it's not potential mgh, it's potential energy Q times V. What about kinetic energy? Grace, does it have kinetic energy? Yes. And how does the potential energy relate to the kinetic energy? We have a conversion of what to what? Potential to kinetic or kinetic to potential, Therese? Is it potential to kinetic or kinetic to potential? Read? What am I losing here? What kind of energy am I losing? I'm losing potential. I'm gaining, so it's a conversion of what to what? If I'm losing potential and I'm gaining kinetic, I'm converting from what to what? Potential to kinetic energy. Right? Exactly the same as it is when the car goes down a hill. So we plug in our numbers and we solve. In this question over here on the left-hand side, let's say we're subbing in a number for HI. What would the value be? What's HI? 100 meters, right? What's HF? Halfway down the hill. 50 meters, right? What about VI right here? What's the initial potential right here? As we're starting going across again. Well, it's like height. It would be 20 volts. What would the final potential be right here? Halfway across? 10 volts. Now, this rears its head sometimes. Maybe in Physics 20 you saw a problem like this. Maybe you saw a problem like this. Wait a second. Is that initial height 100 meters now? Well, maybe it's 200 meters now, and the final height is like 150 now. It doesn't make any difference. In Physics 20, you could do this. You could say, I can define my 0 point anywhere I want. So even if the hill keeps on going, I'm choosing to define my 0 point right here, even if it does keep on going. If my 0 point is here, then my initial height is 100, and my final height would be 50 meters. If I had have went down here, and my initial height was 200 meters, my final height would be 150 meters, which means the difference in height is still 50 meters, and we're still going to end up getting the same answer. Well, the same deal applies over here. We don't know if the initial potential is 20 and the final is 0. It doesn't make any difference. Or 20 and 10, as the case may be. It doesn't make any difference. We know the potential difference between two sides is 20 volts. Maybe it's 20 and 0. Maybe it's 80 and 60. Maybe it's 137 and 117. It doesn't make any difference. Okay? If the initial potential is 137 and the final is 117, then the potential difference is 20. And I can choose to make the bottom of my hill right here, where my initial or my final height or my final potential is 0 and my initial is 20. Does that make sense? Doesn't make any difference. We're going to see a couple questions like that later on today where you're not sure exactly where the bottom of the hill is. Doesn't matter. You define the bottom of the hill wherever you want, as long as you have its height or its potential difference relative to that point. All right, let's take a look at those 4 questions that we had for homework on worksheet number 9. Let's take a look at questions 3 and 4 on that worksheet. 3 says, an electron is accelerated through a potential difference of 9 volts. The electron begins at a speed of 6 times 10 to the 4. What's the final speed of the electron? So this electron is speeding up. That's like a car doing what? If the electron speeds up, it's like a car going down a hill. We want this to be automatic. There's certain things in Physics 30 that we just have to automatically have come to our mind. Force versus time graph, you automatically want to think area equals impulse. You see a funny angle, you want to automatically think, I don't like funny angles. Okay, if you see a charged particle in an electric field, you want to automatically think, I'm positive the force is with the field. If you see a charged particle speeding up, you want to automatically think, hey, that's a car going down a hill. Now, let's picture the car going down the hill. The car is at the top of the hill and has a speed of 10 to the 4 meters per second. Is there kinetic energy of this car at the top of the hill, Ryan? Yes, if this car is moving at the top of the hill, this car has kinetic energy at the top of the hill. Does this car that's at the top of the hill have potential energy? Stephen? Cars at the top of the hill, does it have potential? Yes, except it's not potential mgh, it's potential q times v. Okay, what kind of energy does the car have when it reaches the bottom of the hill? What is it? Is it moving at the bottom of the hill? Yes, therefore it does have kinetic, you're right. Does it have potential when it reaches the bottom of the hill? Well, here's one of those questions that we don't really know, actually. It says it's accelerated through a potential difference of 9 volts. Does it make it to the bottom of the hill? Here's what we know. It makes it across a potential difference of 9 volts. It's accelerated through a potential difference of 9 volts. We don't know what the initial potential is. We don't know what the final potential is. But we know the difference is 9. We can choose to make our 0 point wherever we want. I choose to make it at the end. I choose to make VF 0 and VI 9. I could have chosen to make VF 27 and VI 36. I could have chosen VF to be 6.2 and VI to be 15.2. As long as VI, the initial potential, is 9 more than the final potential, it doesn't make any difference. It's easier, though, if you make VF 0 and VI 9. It just makes the math easier. So let's sub in some numbers here. We've got a mass of an electron of 9.11 times 10 to the minus 31. And VI is VI is 6 times 10 to the 4. Square that. Make sure when you're doing that on your calculator that you use the EE button. Charge is 1.6 times 10 to the minus 19 coulombs. Should we put the negative in there? Never. In an equation, never put the negative charge in there. VI is, we're going to make it 9 volts. Right? We don't really know what it is, but we're defining the point it's relative to. So we're saying the final is 0. The initial must be 9. It equals 1/2 of the mass, once again, times VF squared. Let's do this one on the calculator here, even though I think you guys can do it. Let's say 0.5 times 9.11 times 10 to the minus 31 times 6 times 10 to the 4, second function EE4. Let's square that. There's that first term. Let's add that to the second term using some brackets here. 1.6 times 10 to the minus 19 times 9. There's the left side. And now let's multiply that by 2, get rid of the half. And then let's divide it by 9.11 using the second function EE button. I got a speed here, 3.16 times 10 to the 12 meters per second. Hey, but wait, that's faster than the speed of light. What did I miss doing? Jade, go ahead. What did I forget to do? Yeah, I got to square root it. If you get a speed that's 10 to the 12, 10 to the 13, 10 to the 11, odds are it's because you forgot to square root it. So second function, square root of the answer gives us 1.78 times 10 to the 6. (1.78 times 10 to the 6 meters per second). I promise you, you would get the same answer if you made the initial potential 27 and the final potential 18. Just made the difference in potential 9. 4 says a proton is accelerated from a speed of 5 times 10 to the 4 to a speed of 5 times 10 to the 6. What's the potential difference required to do this? Charged particle speeding up. That's like a car going down a hill. Car's moving at the top of the hill. What kind of energy does it have if it's moving at the top of the hill? Gareth, has it got kinetic energy at the top of the hill if it's moving? It's got potential, yeah. But if it's moving, does it have kinetic? Yeah. So it's got both, right? We're going to say QV potential, not MGH potential, plus kinetic energy 1/2 mv squared equals, well, when it reaches the bottom of the hill, it's just got kinetic energy. Well, how do we know it's reached the bottom of the hill? We're defining the final potential as 0. We're choosing to do that. Whatever we get for the initial potential will be, therefore, the potential difference. If we made the final, we could have put QV in for the final potential energy. Made VF, we could have made it 12. Well, whatever we get for the initial potential, then we'd have to subtract the two potentials to get the potential difference. Makes sense just to make VF 0 then, right? the final potential is 0. And that way, whatever I get for VI will end up being the same value as the potential difference. It's not really potential difference, it's initial potential. But if the final is 0, then the initial is the same as the change in potential or the difference in potential. Okay, so we got a charge here of 1.6 times 10 to the minus 19 times VI plus 1/2 of 1.67 times 10 to the minus 27 times VI squared equals 1/2 of 1.67 again times 5 times 10 to the 6. Let me square that. So get this term, then get this term, and then take this term over by subtracting. And then divide by 1.6. And when you do that, you should get 1.30 times 10 to the 5 for VI. Remember, I just found initial potential, but I defined my final potential as 0. Therefore, the initial potential will be the same thing as their potential difference.